All right. Today we're going to talk about derivatives and integrals of vector valued functions. We're assuming through all of this that we have a vector valued function r of t, which is a curve with three coordinates, f of t, g of t, and h of t, although this could go from one dimension to three dimensions as it is here. So this r goes from r into r cubed, but we could do everything we're doing with two dimensions, so r to r squared. In fact, some of the examples we're going to do are going to be from r to r squared. So from one dimension to two dimensions, or from, in this case, one dimension to three dimensions. First, operationally, I'm going to tell you how the derivative is found, the derivative and the integral. The derivative uh, r prime, or we can use this notation, the r of t with respect to t, is simply the derivative, well, the vector whose components are the derivatives of those functions, the components of the original vector. So we have f prime of t, comma, g prime of t, and h prime of t. So operationally, it is not that bad to figure this out. It's just the derivatives component-wise. Same thing with the integral. We're going to go back and talk about the meaning of those, but first I wanted to show you operationally how this is done. The integral from t equals a to b, although we don't necessarily have to put the t in there, but I want to clarify that we're going from t equals a to t equals b. I guess we can put a t here. Of r of t dt is simply the vector with three components, and the components are, as you may guess, the integral from a to b of f of t dt, comma, the integral from a to b of g of t dt, comma, and then the integral. I didn't have enough room to put all the three components in one line, so that's why the last component has to go down here, h of t dt, close parenthesis, from a to b. So derivatives and integrals operationally are very straightforward. Again, we're assuming we have this function that goes from one dimension to three dimensions. Think of t as the time. And so as time goes by, we are having a curve. So some kind of curve with a direction and some kind of velocity. And in three dimensions, but this could be in two dimensions. And so the derivative is simply defined as the vector with such components, and the integral as a vector also with those components. So let's move on to the meaning of those. Let's start with a derivative. So derivative. As we know, the derivative is defined as the limit as h goes to 0 of r of t plus h minus r of t over t plus h minus t. Of course, the denominator simplifies to just h. There's no need to put t plus h minus t when we know in advance that the denominator is going to simplify down to an h. The reason why I prefer to write it this way initially is because it makes this clear that we have a quotient, a difference quotient. We have outputs that we're subtracting and inputs that we're subtracting as well, and finding the quotient. Um, so what does that mean graphically? If we have some kind of a curve, so this is R, and there is the origin somewhere, it doesn't matter where. So this would be the vector that could correspond to, so R of a t, and then if the curve is moving to our right, then here we have another vector, which is R of t plus h. And the difference would be this vector. When we subtract R of t plus h minus R of t, which is the numerator of this quotient, we end up with this vector. So this vector is this numerator. Oh, this is a little misleading because technically speaking, we cannot divide by a scalar. The denominator is a scalar, it's just numbers. What we mean by dividing by a scalar is multiplying by the reciprocal of the scalar we're trying to divide by. So we're really, we got to be a little careful. The numerator is a vector. It's the difference of two vectors, and that is a vector. The denominator is a scalar. We'd never define what the division by a scalar is, but it is the multiplication of the vector, this vector on the numerator, by the reciprocal of the scalar. Yeah. So when we multiply by this difference, we are taking into account how much time, if we think of t as time, how much time it took to go from here to here. So if it took only 1 unit of time, then this is the vector, that's it. But if it took half a unit of time, then when we divide by a half, we would have to multiply this vector by 2, because remember, dividing by a fraction such as 1/2 is the same thing as multiplying by the reciprocal. So dividing by 1/2 would be equivalent to multiplying by 2. So the shorter the time it takes to go from here to here, the longer this vector is. And the shorter the time it takes to go from here to here, the faster the point is moving from here to there. So again, the shorter the amount of time it takes, the faster it takes to go from here to here, and also the longer the vector. Another way to say that is that the length of the vector tells us how fast the point is moving. Yeah. So magnitude of this vector, no, that's not the vector. After we divide by this, the magnitude of the resultant vector is corresponding to the velocity of the point as the point moves along the curve. So never mind this for now. Yep. Now, if the 2 points are very close to each other, if h is very short, then what we end up, let me draw a new picture. So if we have one here, one vector here, and then the h is so small, as in this case, because we're taking the limit as h goes to 0, that the next point is almost next to the other, then we end up with a very short vector, but a tangent vector, almost a tangent vector rather. And because the h is very short, it's very small, when we divide, we multiply by the reciprocal. The reciprocal of a very small number is a large number. And so we end up with this kind of a vector, which would be tangent to the curve. And the magnitude of the vector tells us the velocity. So now we can say that the magnitude of r prime is the velocity. So we end up with two things. We end up with a vector and its magnitude. A vector and its magnitude. A direction rather, and the magnitude. The magnitude itself is the velocity, and then the direction tells us which way the curve is going at this point. Of course, at this point, then we have a different tangent. And then at this point, then it's going down and so forth. So that is what we mean by the derivative. Let's show some examples of derivatives. Yeah, So example 1a, let's say r of t is equal to 2t, 5t, 3t. So this is a straight line passing through the origin. The derivative at any point is going to be 2, 5, 3. So that means that this is the vector direction at which the straight line is going, which makes sense. So it goes through the origin. When t is equal to 0, we have the origin. And then when t is equal to 1, we are at 2, 5, 3, 2, 5, 3. And when t is equal to 2, we are twice as long. So this vector represents the tangent to the curve. By the way, a straight line has a tangent, and the tangent is itself. So this vector is tangent to the line, which is the curve. That is funny. A line is a curve. And this tells us the velocity. Example 1b, what if we have a different function, 4t, 10t, 6t, as opposed to 3t, 5t, and 3t. So we're doubling 2, 4, 5, 10, 3, 6. The derivative is also called the velocity vector. So the velocity vector, which is the derivative, is equal to, and the second derivative, as you would know, it is the acceleration vector. So the velocity of this curve is 4, 10, and 6, which means that it is going twice as fast as this curve. The direction is the same because if we factor out the 2, we have 2, 5, 3, and that means that we're going twice as fast as this guy at all times. Yep. So it is the same curve, but it's going twice as fast. Yeah. And consequently, the vector that represents the velocity is twice as long. Yep. Let's do a second example that is a little more exciting. So example 2, say we have 2a rather. 4 times cosine of t, 4 times sine of t, 5. This is our r of t equals, and t will run from 0 to 2 pi. So as you're familiar with, this is a circle suspended 5 units above the origin. So, and it starts at 4. So this is 4 units, it goes up. That's where the circle starts, and it goes around this way. And the radius is 4. 4 is the radius. So this point is 4, 0, 0. And then this is up 5 units of where it starts. Oh, it goes in this direction. And if we didn't know that, we will find out soon. So this point up here would be 4, 0, 5. And then we have a circle with center at 0, 0, 5. So the center would be here. And then we go around. So the derivative r prime of t at any time will be the derivative of cosine, of course, is negative sine. So we have negative 4 times sine of t, comma, 4 times cosine of t, comma, 0. The derivative of 5, of course, is 0. The derivative at 0, so at that point, this is the point when t is equal to 0, would be sine of 0, so 0, comma, cosine of 0, which is 1, but then we multiply by the 4, so we get 4, comma, and 0, of course, is 0. So at this point, the velocity vector or the tangent vector to the curve at this point would go in this direction, 0 units. So that means not going towards the z-axis or away from the z-axis, but rather parallel to the y-axis, 4 units. A top view of this. So we have the circle, and let's say this is the x-axis. So x positive and y positive, and the radius is 4. Pretend that it's a circle. So the reason why this looks kind of funny is because, again, this is the positive x-axis, this is the y-axis, that is the z-axis. So I'm assuming, or I'm pretending like I'm moving this in such a way that I see the x-axis going down, and or I'm moving up so I can see this from the top. And as we see this from the top, then the x will end up towards our bottom. And then, oh, this is interesting. The tangent vector is going to go 0 units in the y direction. So from this point, no, and then no x up or down, but 4 units in the y direction. Remember, the radius of the circle is 4, so it will line up with this. And then it is not going to go up or down. So this is the tangent vector to that curve at that point. This is example 2a. Let's look at example 2b. R of t equals 4 times cosine of 2t, 4 times sine of, 2t, comma, and then 5. I did not have enough room to put the 5, so 5. It is the same, this is intended to be the same problem for cosine, for sine, and 5, except that we are changing the t in example 2a into 2t, and that, as we know, causes the circle to be drawn, same circle to be drawn faster, twice as fast. And consequently, we don't need as much time to draw a full circle. We can go from 0 to pi, half the time. So this circle, if t was measured in seconds, would go from 0 to 6.28, why 6.28? Because pi is about 3.14. So when we multiply by 2, well, that's approximately what pi is. So this is 6.28 seconds. So it takes about 6.28 seconds to go around. So 1, 2, 3, 4, 5, 6.28, boom, and we go back. So that's what took to go all the way around. This circle is going to be exactly the same circle, except that it will take way shorter to go around. So it will take half as much, 3.14, because that is about 3.14. And if we are talking about seconds, it will take 1, 2, 3, as opposed to 1, 2, 3, 4, 5, 6.28. 1, 2, 3.14. So this is going to go faster. The tangent vector is expected to be almost the same, except that it will be longer. Notice I put some ellipses here indicating that the vector actually goes farther before it stops. It is a finite vector though. Let's do the derivative. So r prime of t in this case will be 8, because we're using the chain rule, 8, I'm missing a negative, sine of 2t, comma, 8 cosine of 2t, comma, and 0. So that means that the vector that is tangent to the curve, in this case, doesn't go up or down. It stays completely horizontal because of this 0. All right, r prime of 0 will give us 0, comma 8, comma 0. So we have the same vector as in the example 2a, but instead of being 4 units long, as in this case it will have 8 units long. So from the top, we have a circle again, and when we find tangent, so this is a top view, this is the positive x-axis, positive y-axis, this is 4 units, so the tangent vector is going to be twice as long, because assuming this describes a particle that moves along this motion, or along this path rather, this particle will be moving twice as fast, and consequently the tangent vector would be twice as long. If the particle was moving in the opposite direction, then the tangent vector will be pointing in the opposite direction. There are some examples with curves that are not perfectly horizontal. I'll let you work those out. Let's talk about integrals. Before we start integrals, I want to remind you of averages. So when we find the average of two elements, two things, it doesn't matter what they are. So let's talk about average in general. That is, as A and B, if you have two, you add them together, divide by 2. Another way to think of this is that we have a half A plus a half B, if you distribute the division. And something to notice about this is that a half and a half is add up to 1. If you have 3 elements, or if you have, so average of 3 elements, we have A plus B plus C, divide by 3, and that is our average. Another way to think about that is a third of A plus a third of B plus 1/3 of C. And notice that the coefficients we're using add up to 1 unit. That is very, very important and relevant. And then we have weighted averages. So for instance, weighted average would be, let's say you want to put more weight on what A is, so you can put 3/4 on A and 1/4 on B, and that is a weighted average where you're putting much more weight on the value of A than on the value of B. The key here, though, is that those two add to 1. Yeah. So again, we're putting way more weight on this. So on a regular average, we're putting the same weight on the elements that we are averaging. So in this case, a third, because there's 3 of them, same weight. But we have a weighted average, which is not a normal average, in which you are putting more preference on one versus the other. Well, we are going to extend this to vectors. Vector averages. That's a very, very important thing to know and how it works. So you have the origin, you got a vector A, and then you got a vector B. The average of the two is going to be, the normal average is going to be the vector that is in the middle, right about there, in the middle of the two. So this is going to be vector A plus vector B, B, divided by 2. Divided by 2. This is kind of weird because technically speaking, we don't have division by scalars. We have multiplication by scalars. Remember, this means a half of the quantity A plus B, which makes more sense. If this is a vector, we may multiply by a scalar. And so we're multiplying by 1/2. We have weighted averages. So if you have the vector A, the vector B, the origin somewhere, there, If you put 3/4 A plus 1/4 B, let's see, that's gonna put us 3/4. We're gonna be more A than B. So if you join the line between A and B, this point, the point 3/4 A and 1/4 B is gonna be a quarter away. That's kind of weird from A, because this vector, this one vector, which is this one, is gonna be more A than B. So that's an interesting thing to do. And then you can average all kinds of vectors. They don't have to be on a line. You can average 3 vectors and so forth. So now let's talk about integrals. Integrals. So what is an integral? An integral of r of t dt from A to B. By the way, when we write down the differential, and please always write down your differential, that differential tells us the nature of those integration limits. So in this case, this is telling us that we start when t is equal to A and we end when t is equal to B. So this variable, but it's the reason why we know that is because of the differential. The differential declares what those two variables refer to, or rather what those two numbers refer to. They refer to t because we are integrating with respect to t. Yeah. And that may or may not have something to do with this one, with this variable. Usually it does, otherwise we're integrating a constant, or a constant relative to t. So what does that mean? Remember from calculus 2, or calculus 1 for that matter, this is the limit. There's a couple different ways to define this, but let's assume we're using a partition, and the lengths of the intervals of the partition are constant, rather are equal. So we can just say as n goes to infinity of the sum, a Riemann sum, although here we have a vector, but it's equivalent to a Riemann sum from I equals 1 to n. And then we multiply the values, the outputs of the function are of ti. And you can take, if the function is continuous, you can take any value of t. Again, I did say if the function, so let's just say that. Let's write it down. Assume for now, assume r is continuous. Yeah. So we multiply this with delta t, so little bits of t's. Yep. So these are periods of time. Yeah. So we multiply a vector times a little bit of time, and that gives us the what we are adding together, and then we take the limit as that sum goes to infinity. So this is what the integral means. And the reason why we may want to see it this way is because then we can have a geometric interpretation of the integral. We're going to do a whole bunch of examples, easy examples. Okay, so let's start with example 1a. R of t will be just t, comma, 5. By the way, this is a vector function that goes from r, so comma r, goes from r1 to r2. So this is to simplify what I'm doing. I'm just going to go in and do this in 2 dimensions. We can do this in 3 dimensions. We will have 3 coordinates instead of 2 coordinates. So what does that look like? This is just, if this is the origin, again, we're in 2 dimensions. We just have a straight line going by 5. So if this is 0, 5, then we go in this direction. So So there it is. We have a straight line, horizontal straight line. This is the x-axis, positive x-axis, positive y-axis, and we go straight. I should have put this in a new sheet of paper, but it doesn't hurt to copy this over. So again, example 1a, r of t equals t5, and I already did the picture. So what does it mean when we take the integral from 0 to 1 of r of t dt? This r of t. By the way, sometimes I will write it this way, and sometimes I will write it t5, close the parenthesis, so that's a vector, dt from 0 to 1. So please do not get confused. Those two are exactly and identically the same thing. Let's do this operationally. So what you have to do is what you did in Calc 1 or Calc 2. What is the integral of t? Well, the antiderivative of t using the fundamental theorem of calculus to figure this out. T squared over 2, 5, 5t, the antiderivative. And we're going to do that from 0 to 1 as t goes from 0 to 1. So at 1, we're going to end up with 1 squared over 2, a half, and 5 minus, at 0, we're going to end up with 0, 0. So we end up with a half 5. Okay, so the integral of this vector function is from 0 to 1 is 1/2 5. What does that mean? It is relevant to notice that we're going from 0 to 1. Going back to the definition, what we are doing is adding a whole bunch of vectors and multiplying by equal lengths. But because we're integrating from 0 to 1, these lengths add up to, from 0 to 1, add up to 1. Because remember, t in this definition, sorry to squeeze this in here, but if there is t, and there is a and b, and this is the t-axis, which is not part of the graph, it's outside of the graph, this is time. Each one of these delta t's is just one short segment. And we're assuming for now that they're equal length. In a more general definition of integral, they don't have to be equally length. They don't have to be the same length, but we're going to assume they are. So what we are doing in this case is okay, let's draw the picture. Sorry too. So there's the picture. The units are going to be off. This is not going to be proportional correct, but this is 5. This is the origin. I'm going to assume this is 1. Again, this is not proportionally correct because if this is 1 unit, it doesn't make sense that this is 5 units. So the units are off. The x-axis units do not correspond to the y-axis units. But the picture looks better this way. That's why I do it this way. So this function up here means that we have the vector 0, 5. As we run from 0 to 1, we got 0, 5. So we have this vector. When we reach 1, we have this vector, and we have all the vectors in between. And we're going to multiply by little bits of this interval from 0 to 1. So we're going to, when we multiply by little intervals, all of these vectors get shorter, get really short, and then we're averaging them. Rather, we're adding them together. The other way to say it is that we're averaging all these vectors. When we average all these vectors, we get the middle, which is exactly this. So in a way, the integral of this, if we do this from 0 to 1, gives us the average of all the other vectors. Isn't that interesting? This works if the curve is a straight line really well. If not, then it still gives some kind of an average. We still end up with some kind of an average. But then we have to take into account different velocities. This has a nice uniform velocity, so we're good. Let's do a second example. Example 1b. What about the integral from 1 to 2 of the same function, of the same t5 dt? So again, we have t squared over 2. So I'm going to continue here. T squared over 2, 5t from 1 to 2. So at 2, we're going to end up with 4. At 1, we're going to end up with 1. So we get 4 minus 1 over 2, comma. At 2, we get 10. At 1, we get 5. We subtract, and we don't divide by anything. So we end up with 3/2, comma, 5. And you know what is interesting? If 1 is here and 2 is here, and there is 5, and this is the first vector. Oops, sorry, that's not the first vector. This is the first vector, and this is the last vector, and we have all the vectors in between those two. The average of all of those will be in the middle, as this shows. And the reason why this works well is because we're using an interval from 0 to 1. Well, an interval for which the delta t's add up to 1. So even though we're going from 1 to 2 in this case, the delta t's before we take the limit add up to 1. So we have a nice average. Yeah. What if we do from 0 to 2? So example 1c, integral of r5 dt from 0 to 2. I'm sorry, I didn't mean r, I meant t. Let me double check to make sure I put t's, yeah, t comma 5. So this is t comma 5, same function, but we're going to 2. So this is t squared over 2, 5t. This time we're going from 0 to 2. So at 2 we get 4, divided by 2 is 2. And, 10. Because we don't subtract anything. All right, so we have the same picture. 1, 2. The first vector is this one. The last vector is this one. The average would be here. It would be 1, 5. Remember, this is 5. So that would be the average of those two. The reason we are not getting the average is because we are using a longer interval. We're going from 0 to 2. So that is extending the average out. So we still end up with the same direction as the average, but it is twice as long. Instead of 1, 5, we end up with 2, 10, which is twice as long. Sorry to overlap my picture into this math, but that's what we get. We are exactly on the same direction as the average rather. I think that is very exciting to see how the integral gives us the direction of the average of the vectors. But there are more examples to show. Let's do a different example. 2a, what if we integrate from 0 to 1 t squared dt? This is a trivial parametrization of the parabola from 0 to 1. 0, 0, when t is equal to 0. This is a little confusing because 3 things are 0, 0, 0, 0. And then this is 1, 1, 1. So 1, 1 is the actual vector where we end, but then t is equal to 1. So the question is, what is the average of this? In a way, because we're going to be multiplying. Oh, the pictures gets kind of fuzzy because we have this vector and this vector and this vector and those vectors, and we average all of those vectors in between. And where does that go? Because we're given equal weight to all of those vectors. Well, we can just do the integral and find out. So the antiderivative of each one of those components is going to be t squared over 2, t cubed over 3, from 0 to 1. Plug in 1, we get a half and a third. Plug in 0, you get 0 and 0. So we end up with a half, a third. So let me draw a bigger picture of this situation. There it is. So the average of all of these vectors, and by vectors we mean all of those, is going to be a half, which is interesting, half the way, a third, which is above the curve, but below this line. So it is about there. That is where we have the average of all of those vectors. So the coordinates are 1/2, comma 1/3. The point on the curve corresponding to 1/2 is 1/4. The point down here is a half, comma 1/4, because we square that and we get a fourth. The point corresponding to the straight line joining the first point and the last point on the interval is 1/2, 1/2. So that is above, 1/3 is below, and 1/4 is even lower. Yeah. Yeah. So this works really well if we go from 0 to 1. If we reparameterize, so let me go back to example 1. So this was example 1C. Let's go back to 1D. There's no going back. Let's go forward to 1D. 1D. What about integrating 2t comma 5 dt from 0 to 1/2? Okay, so this is the same line as before. There's the 5, and we go from 0.5 to 1.5, but we're going twice as fast. This is faster than example 1A. So are we going to get the average in the middle? Let's figure this out. Okay, so this is going to give us t squared, 5t from 0 to 1/2. So we end up with 1/4 and 5 divided by 2. So the average between 0.5, or the midpoint rather, between 0.5 and 1.5 would have to be 1/2, 5. But we didn't end up with that. We ended up with 1/4, 5/2. So if this is a half, 1/4 would be here. 1/4 and half. Yeah, we end up with exactly half of what we expect the average to be, because the interval has been modified. This is really, really interesting. What we did is slow down, rather, we went faster from here to here, and that makes the average shorter. If you slow down, that makes the average longer. Notice that we are going in the same direction, though. I find that very, very fascinating, that we end up with some kind of average vector. Let's do 1E. And one of the reasons why I like math was because experimenting with math is very, very inexpensive and safe. If you're in chemistry, if you want to change one component in your solutions, well, you have to buy that component, and then you have to mix it up, and then who knows what's going to happen when you mix things up. I don't know if they're going to explode or whatever. But with math, you can just change a component in our solution, and all you're doing is using a little more paper and ink, and that's it. And you can do your experiments very cheaply and easily. So I'm going to do an experiment right now. I'm going to change the path. The path is the same. I'm going to change how it is drawn. How about t squared and 5 from 0 to 1 with respect to t? Yeah. Notice that I'm saving a step. Many times people would do this. Let's say r of t is equal to t squared comma 5, And then let's find the integral of r of t dt from 0 to 1. Instead of doing those two extra steps, telling you what the function is and telling you what the integral is that we want to find, I'm just doing all of that in one step. And this is the function that we're integrating, and there's the integral. Okay. So this is the same line as before, from 0, 5 to 1, 5. This is supposed to be horizontal. It looks not too horizontal. And the question is, what are we getting? Oh, what is happening here? We're using t squared. So that means that at the beginning, the particle, the point is going slowly, and as it continues, it speed ups, and then it ends up faster than how it started. So slow, and then faster and faster and faster. Yeah, slow and then faster. So that means the intervals of time here, well, let's see what the interval is first. So this integral is equal to t cubed over 3, 5t from 0 to 1. And that's going to give us a third comma 5. Ooh, so if this is a half, now we're closer here. So we're not getting the middle as we did earlier with the same kind of picture. We're getting closer to this. We're getting more of this, which makes sense because we spent more time on here. So there's, in a way, more vectors on the left because we spent more time drawing vectors on the left. And here we have to draw them faster. So that means there are fewer because my drawing is going at the same speed. So if I move to the right faster, there's going to be fewer vectors to be drawn. And that's why we get more of this than that. Very, very interesting. And you can play with this. Yeah, so one thing that you could do, 1f, which I'm going to let you do on your own, is, for instance, the integral from 0 to a half of the quantity 2t squared, comma 5 dt. And then interpret that. So this is going to go slow and fast at the end, but it is going to take half a second, assuming time is in seconds, half a second to do this drawing, as opposed to 1e, where it takes a whole second to go there. So now we're going to go faster. What does that mean? That's something for you to do. So please do this one and interpret it. Yeah. So that is derivatives and integrals. And with this, we'll stop this video. With this, we'll stop this video.